Hello everyone! Today we're going to do a little review of 7.1 and 7.2, hopefully clarify some things about slope fields and make this a little bit easier for you to identify the slope field graph with its equation. We will also practice a couple of AP free response question types so you become more familiar with that and the format that you'll see on the AP exam. So to begin, if you're following along in your Pear Deck, please fill out this question, what you're hoping to clarify in today's lesson. It is my hope that we will go over it in this video today, but if we don't, then I'll read your response here and I'll be able to follow up in class on anything that we haven't. So let's go ahead and get started with a little matching review worksheet. It is very common on the AP exam that you would see this type of question on a multiple choice, and I want to give you some key hints to be able to do these questions really quickly, especially the matching type questions. So what I'm going to do first is on this particular worksheet, there just isn't some of the key points drawn in, like the undefined and where it's 0. And that's really important for you to draw in on the AP exam. And so on this one, you can see, obviously just by following the curve, that it's kind of like circular things. So these should have been undefined here. On this one, it's not drawn in. I think you just can't see it on the printout, but these are horizontal there. And then on this one, they should also be horizontal. And I know these things just by kind of looking at the shape of the curve. And so that's how I'm drawing it in. But as you're sketching, please make sure to always do horizontal and vertical little sketches, because oftentimes on the AP, they give you an entire point just for drawing that. So that's very important. Now, the next thing that I want to do is I want to identify which of these graphs depend only on X or depend only on Y if I can do that. So I'm going to start with which ones depend only on Y. Depending only on Y would mean when the Y value changes, the slope field changes, but it doesn't depend on the X. So this is an example of that, slope field 2, and I'm going to just write only Y. And the way we know that, again, is look, they're the same exact thing on all of the rows, right? Only when the Y value changes, the slope change. See, it doesn't matter if it's at -5 or at +5. I have the same slope as long as Y equals 0. Again, X equals -5 or X equals 5. It's the same slope as long as Y equals 1. It's only when the Y value changes that the slope field changes. Contrast that with slope field 1. Look at this. They're the same in all of the columns. So only when the X value changes is the slope field changing. The Y value doesn't affect anything. So this one would be only X's. Now, let's contrast that with this one. You see, when the Y changes, my slope field is changing. When the X changes, my slope field is also changing. This one depends on both X's and Y's, right? So that's why I don't see anything the same in the columns or in the rows. Now, let's look at this one. Only when the Y changes am I changing slope fields. So it only depends on Y. On this one, both. On this one, both. On this one, both. This one, only Y. Now that I've labeled that, I'm going to go ahead and look for my favorite thing, which you probably know by now, which is where the slope fields equal 0. So I'm going to take the ones that are only Y first. So which ones only depend on Y? This has an X and a Y, XY, 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 only X. So this one is probably my blue one. We'll come back and check that in a minute. Only Y, only Y, only Y. All right, so as I said, let's see where these slope fields, where the dy dx actually equals 0. So dy dx equals 0, set this equal to 0, when what? When 0 equals y over 2. In other words, when y equals 0. Which of these graphs, I only have 3 to choose from, only flattens out when y equals 0. See, this one flattens out at 0 and at 4. 0 and 4. This one only flattens out at 0, and this one only flattens out at 1, 2. All right, so this one must match with this slope field 4. Now let's move to this one. When does it flatten out? Dy dx equals 0. When 0.25y times 4 minus y equals 0. In other words, when the 0.25y equals 0, or when the 4 minus y equals 0. In other words, when y equals 0 or y equals 4. Aha, that's this one, wasn't it? 0 and 1, 2, 3, 4. It was 0. Great. So that's going to be slope field 10. And then the last one, that's clearly 0 when 2 minus y equals 0. And that's exactly what this one was doing, wasn't it? So that's going to be slope field 2. Now let's verify that this one matches with this one, which was what we were thinking. So this one, dy dx, is going to be equal to 0 when what? When 0 equals x. So is that true? Sure is. Along x equals 0, we have all flat tangent lines. And then look, when x equals 1, isn't the slope 1? And then when x equals 2, doesn't it look steeper? So that's like 2. And that's exactly what this one's saying. This one's saying that the slope is just equivalent to the x value. See, when it's negative 1, it looks like a slope of negative 1. So yes, indeed, that one checks out slope field 1. All right, now we did the easy ones. Let's go back and tackle all the rest. So I'm going to start by looking over here at what we have here because look, on this one, I see some nice properties. I see that it's going to be equal to 0 and undefined because it's a fraction. dy dx is going to be equal to 0 when what? When x over y equals 0 and a fraction equals 0 whenever the numerator equals 0. So that would be whenever x equals 0. And while we're at it, let's also look where dy dx is undefined. It's undefined whenever the denominator equals 0. In other words, when y equals 0. So which of these graphs is undefined? And an undefined tangent line would be vertical, right? That's where a slope is undefined. So it would be going up and down along y equals 0 and then flat along x equals 0. That looks precisely like what that one is saying. But you know what? There's one more and I forgot to draw in the undefined. Could also be this one. So we got to tell, is it 5 or is it 6? So the easiest thing I think to do is to just put in another point. Let's put in the point 1, 1, because this one's going to be positive and this one's going to be negative. So at 1, 1, we're going to have dy dx equals x over y, which would just be 1 over 1. So in this case, it should be 1. And so which of them is a positive 1 at 1, 1? This one is, right? So this must be slope field 6. And we're thinking, you know what? This was so close to being this one. Is there any other that's x over y except negative? It is. You see how this is just negative, so that's why at 1, 1 it would be negative 1. Everything that was positive in here would just be negative in here, and that's exactly what's happening. So that's going to be slope field 5. All right, now my pen is not working well, which is why my handwriting is so messy right now. I'm going to restart my computer, come back, and hopefully my tablet will be working better then. So I'll see you in a second. All right, I'm back, and hopefully my pen is going to work better now. Let's see. Let's continue with the same kind of thought we had there since we were tackling these ones with a fraction. Why don't we just tackle this one while we're at it? We can see dy dx. Oh, my pen isn't working any better, so sorry, guys. This is going to be a video without perfect handwriting. I think it's going to be more about me dealing with it than you dealing with it, to be honest. So, all right, we are going to have the slope equals 0 when the numerator equals 0, the negative y equals 0, which is the same thing as y equals 0, right? And then it's going to be undefined when that denominator equals 0, whenever x equals 0. Do any of them look like that? Look at this one right here. Again, it's not drawn in, but you can see the pattern. It looks like it's up and down here, and it's flat there. Whenever x equals 0, it's undefined. Whenever y equals 0, it is flat. And then let's just check a point for good measure. When we have 1, 1, it would be negative 1 over 1. So at 1, 1, does the slope look like negative 1? Yeah, it does. So that's a good little check to just check one point. And so that's slope field 7. Okay, now we only have 3 more to tackle. So this one, when is it going to be 0? It's going to be 0 when x minus y equals 0. In other words, when y equals x. So along the line y equals x, so that would be this line here. Whenever y equals x, our slopes should be 0. Oh, look at this one. Doesn't that look like they're zeros? These are all zeros along the line y equals x. That is the line y equals x. Let's see if any of the other ones are like that. Oh, this one is too, isn't it? And this is the only other one that we haven't tackled yet. And this one looks like it's going to be all zeros along the line y equals negative x, right? So let's stick with this one. Let's put in a point. In this one, if we put in a 1, 1, we're going to get 1 minus 1, which is 0, which isn't going to be super helpful because we've already tackled that. So why don't we, instead of picking 1, 1, pick 1, 0? We would get dy dx equals, at 1, 0, that's going to be x is 1, y is 0, 1 minus 0. So we should get a slope of 1. And again, we were choosing between this one and this one because on both of these, they were zeroing out along the line y equals x. So at 1, 0, so that's this point 1, 0, this one's negative 1, which wasn't what we wanted, but this one was positive 1, which was what we wanted. So this one's going to match up with this. So this is going to be slope field 3. And then we're choosing between this and this. And which one's going to be 0 at y equals x? You see this one's going to be 0 at y equals x. This one's going to be 0 at y equals negative x. So this one's going to match up with this one. And it's just getting too hard to write here, so hopefully you're following along with me at this point. And then this one is going to be 0 at y minus x equals 0. In other words, y equals x. And then if we look at the point 1, 0, we're going to get 0 minus 1 in this case because the x is 1 and the y is 0. So we would be getting negative 1, which was precisely what we got in this one. So this is going to be slope field 8. And that's really how you tackle these problems. All right, hopefully it's going to be a little bit easier to write now that I have more room in this one. So this is an actual AP problem from 2007. It says, first of all, just sketch out the slope fields. So this is what it'll normally look like. They might ask you to fill in like 6 to 9 points, and you just literally put in the x and the y values that they ask you for. So in this one, I'm going to be looking at the x, the y, and then see what my dy dx value is so I can sketch in the slope. At negative 1, 0, which is my first point there, negative 1, 0, I'm going to have 1/2 times negative 1, negative 1/2 plus 0 minus 1, which is negative 3/2. So a 45-degree line going down would be a slope of 1, and I want it to be just slightly steeper. That's what I do. Now let's look at this point, negative 1, 1, negative 1, 1. That would be negative 1/2 plus 1 minus 1 would just be negative 1/2. And so again, 45-degree line, but a little less steep than that. Then let's look here at negative 1, 2. Minus 1/2 plus 2 minus 1 would be just positive 1/2. A slope of 1 would be 45 degrees, but about half as steep would be like that. You would just do the same thing for all the other points. So I'm going to do it a little bit quicker. 0, 0 would be a slope of negative 1. 45-degree line going down. 0, 1. 1 minus 1 is 0. So that's going to flatten out, and make sure you draw that in. 0, 2 would be a slope of 1. 45-degree line, slope positive. And then I'm going to draw in the rest without talking it all out because hopefully you get the point. It's just plug it in. There's no faster way to do that. All right, now on this part B of the same problem, I just needed more room. This means the second derivative. Find the second derivative. So they already found the first derivative, so I'm just taking another derivative. And you have to know that notation for second derivative. So if you've forgotten it, please refresh your memory. The derivative of 1/2 x is just 1/2. The derivative of y, though, every y has an x in it, so the derivative is 1 times y prime, and then the derivative of 1 is just 0. Now, this says, give me the second derivative in terms of just x and y, but I have a y prime in here, which is not okay. So what you need to recognize is that what they've given you here is y prime. And so you're going to plug this in for y prime to simplify. 1/2 plus 1/2 x plus y minus 1, which is 1/2 minus 1 is just going to be minus 1/2. So I'm going to be left with 1/2 x plus y minus 1/2. And that's going to be my final answer for the second derivative. However, they also asked us to describe all solution curves where it's concave up. So we know concave up when what? When the second derivative is greater than 0. So we need to see where this guy, the 1/2 x plus y minus 1/2, is greater than 0. And we just want to solve for y. So scoot everything else to the other side. Whenever y is greater than negative 1/2 x plus 1/2, our solution curves are concave up. So that would be our solution. That also means anything above the line y equals -1/2 x plus 1/2. So you could write it either way is great. And then part C asks for a particular solution, which is what we're going to dive into when we get to 7.3. So we're not there quite yet. We'll come back to this problem soon, but at least we were able to do A and B for now. Now, I just want to do a quick little review of distance, displacement, and average value, kind of seeing them all together and making the best use of our calculator as possible. In part A, for what time values is the object at rest? The object is at rest whenever the velocity equals 0, and they give us the velocity here. So let's go ahead and just factor out a 3t. In other words, when t equals 0 and when t equals 2 seconds is our units in this one, our object is at rest. And this is the type of explanation, justification we want to be giving for the AP exam. Now, when they ask us total displacement, I'm going to do this two ways. First of all, I'm going to do it entirely on the calculator if I have a calculator, because total displacement is simply the integral, in this case from 1 to 4, and for displacement, it is just the integral of velocity, versus total distance is the integral of the absolute value of v of t dt, because remember, we want to count up all of our, like if we're going backwards and forwards, we want to count up all the steps backwards and forwards, but displacement is where are we in relation to our original position. So they're different questions. Now, if I have my calculator, I'm just going to math 9 it, and I'm going to show you how I'm going to do it. I'm going to put in y1 that 3t squared minus 6t. Then I'm going to go to my home screen, and I'm just going to math 9. I'm going from 1 to 4. If I'm doing displacement, all I'm going to do is vars and go over to y vars, select y1 and dx, and that's going to be my answer, 18 meters, because I had meters per second for velocity, so meters. And then to do the total distance, let me just go ahead and grab the same equation, just press enter to pull it back up. And then instead of just y1, we want absolute value of y1. So I like to find that in catalog because it's the first thing there, y1. And so that's going to be 22 meters. This one is doing a little bit of rounding here, but accurate to 3 decimal places is 22 meters. And I also just want to, for a refresher, go ahead and do this if we didn't have a calculator, because it could be on the no calculator section. So how we would do this is displacement is pretty easy by hand. So we would be doing the integral from 1 to 4 of 3t squared minus 6t dt, antiderivative of 3t squared, leave the 3, add 1, divide by what we added, minus, leave that 6, add 1, we have squared, and then divide by what we added, and then we're evaluating from 1 to 4, and so we would have, look, those cancel out beautifully, just t cubed minus 6 times 1/2 is 3, t squared from 1 to 4, and so you would have 4 cubed minus 3 times 4 squared minus, then put in a 1, you would have 1 minus 3. And then, you know what, if you have to do this in your head, it seems a little bit hard because you don't want to have to do 4 cubed, but you could think of it as like I could take a 4 squared out and then I just have a 4 minus 3 left, minus -2. And so then that's just 1. So this is just 16. And then it becomes easy. 16 plus 2. You have to start being able to do some mental math. So we actually just get 18 meters that way again, which is nice if we think of it like that. Now, the total distance is a little bit harder. How do we know that one? Well, we need to separate the forwards and the backwards movement. And in this part right here, we had found the object is at rest. The velocity is 0 at 0 and at 2. And we would actually be going from negative to positive there. In order to do this, we want to separate our backwards movement. So we would be going from 0 to 2, but in this case it says start at 1. So we're going to go from 1 to 2 of the velocity function. Make that positive because we want to add everything up, plus the integral from 2 to our ending, which is 4 of v of t dt. And we don't really need absolute values around this because we already know it's positive, but if you like doing it, go for it. It's not going to change anything. And so if you were to work that out, you should get the same 22, but that's how you would do it by hand. And then you would be putting it into, of course, this equation right here. So basically t cubed minus 3t squared from 1 to 2. Make sure that's positive, your answer. Add it up with, evaluate this one from 2 to 4. That one is going to be positive. And when you add them up, you should get 22. Now, average velocity, they want the average velocity, and they give you the velocity function. So that is the average value. So that would be 1 over b minus a integral from 1 to 4. So the reason that we know that we're doing the average value is just because the velocity function is given to you. If they were giving you position, then average velocity would just be a slope, but they're giving you velocity. So don't go finding another antiderivative because we already solved this question up here, right? So now we're just going to do 1/3 of 18, which is 6. And our units, the integral is meters, but then we're dividing by seconds. So it's going to be meters per second. And you know average velocity anyway is measured in meters per second. And then in part E, they say if at time 1, the object is 2 meters from the origin, so that means the position at time 1 is 2, then what is the position at 4? They want us to know S of 4 equals what? You see, they are giving us the velocity and they want to know something about position. So we know to get from velocity to position, we're doing an antiderivative. And what do you think we're going to use? Look, they're telling us something about 1 and they want us to find something about 4. So we're probably going to use 1 and 4 as our bounds, okay? And so the integral from 1 to 4 of v of t dt, well, yes, I know we've done this like now 1, 2, this is the 3rd time. We know that this is 18, but what does it represent? This represents, the antiderivative of v is s of t, isn't it? From 1 to 4. Isn't that s of 4 minus s of 1? And didn't they tell us that s of 1 is 2? So isn't that, I'm going to go backwards here, s of 4 minus 2? Because again, they gave us s of 1 is equal to 2. So can't we now solve for s of 4? Because we know this part's 18. Put it all together. 18 equals s of 4 minus 2, which means that s of 4 is 18 plus 2, or 20. And our position is in meters. So our answer is going to be 20 meters. So it's 20 meters from the origin. And that's it for this lesson. I hope you found this helpful. Bye.